Be right back.
A lot of water.
Sorry guys, I have to go get some paper. Once again, they're out. All right. Now we can actually begin. Okay, so what we're going to start talking about today is estimation theory, which is sort of the complement to what we've been discussing so far. So the main idea here is that we're given a sequence of data, x0, x1, and so on. And there is a particular parameter value that we are interested in, and what we want to do is, in some sense, find the best estimate of some parameter of interest. And of course, this parameter of interest, let's call it theta, this is somehow related to these data points that we have. So the idea is that the estimate for this parameter is going to be some function of the data, and we're generally going to denote it by theta hat, which is some function g of this data, x0, x1, and so on. Okay? This is n minus 1 here. This is n minus 1. Okay. So as an example of this, let's say you collect a bunch of data, x of n, which is some constant plus noise. Okay, and this constant, let's say, is unknown. Okay, and these guys are noise values. As an example of this, one thing you can do is basically just take the data points that you have and average them together, right? There's no reason to think that that's a very good estimate. Whether that's a good estimate or not is going to depend on the characteristics of this noise and so on and so forth. But for instance, you might have a hat equals, let's say, 1 over n sum of these xn's. Okay? This is one choice, so then this function here is your g of x0, x1, xn minus 1. Okay? Now, how does this fit into the general picture of things that we talked about in the previous lectures? Well, let me give you a general example of where this kind of thing comes in handy. So, for instance, suppose you have, this is an example that I think I mentioned in the first lecture. This is the cruise control system for a car, right? Okay, so the idea behind cruise control is that you set the speed, and the car is supposed to keep you fixed at that speed, and you don't have to do anything. Right? Just sort of sit back, and the car will move at this constant velocity. So how does this work? There's a bunch of blocks that take care of this. So the first one is a fuel injector. This is the thing that decides how much fuel should be injected into the pistons, which controls the rate of firing. So this fuel injector is running the engine, and the engine, of course, is turning the wheels. Okay? And this is going to produce some velocity, right? Now the idea is that you want to keep this velocity fixed. And in order to be able to do that, you have to measure this velocity. Right? So what you're going to do is you're going to take the wheels, and you're going to measure how fast the wheels are turning at any given point in time. And you're going to have a box here that's going to estimate the velocity. Okay? Now, here, you're going to take this estimated velocity, and you're going to compare it by basically subtracting. So plus and a minus here, a v star. Okay, this v star is the reference speed that you want the car to be moving at. So let's say you set it to go to 65 miles an hour. And so the estimated speed from the wheels is going to be compared to the ideal speed. And then you're going to generate an error. Okay, so this is the error. And then this error is going to go into a box, which is called a compensator. And that's going to tell the fuel injector whether to inject more or less fuel into the engine. Okay? So this is a loop. This is basically the control loop that takes care of a fixed velocity. And this is the command that you give it. Right? Now what you can see here in this thing is that it is absolutely critical for you to have a reasonably good estimate of this velocity given what you're measuring from the wheels. Right? So if this estimator does not do its job, this critical part, if this critical part doesn't do its job, then this whole feedback loop is going to fail. Okay? So this is an example of where you would take a bunch of data, and from that you would estimate a velocity theta hat, and that would be the box here, and then you would complete this loop. And of course, this is just one simple example. There are literally thousands of examples around where the estimation part is going to play a very key role in terms of how an overall system operates. Okay, so given this framework and these two simple examples, let's ask some fundamental questions. So suppose, again, I consider the general case, this G, and I'm going to write X here. This X here is going to contain all the data, right? So this is just going to be a vector, say X0, X1, and so on. Xn minus 1. Okay. So now that I have this formulation, I can ask what is the best choice for G? What is the best, and I'm going to put this in quote. The reason I'm going to put it in quotes is because I haven't defined what I mean by best yet. Okay, so you remember in the detection scenarios we talked about maximizing the probability of detection for a fixed false alarm. That was one optimality criterion. We talked about maximizing the output signal to noise ratio. That was another criterion. So what's my criterion for deciding what's best here? I haven't defined it yet. Okay, I'm just saying I'm going to define some criterion, and then I'm going to try to find out the best G according to that criterion. So now if I have done that, how would I find G? So as you can imagine, for some choices of an optimality criterion, it's going to be easier to find G than it is for others. And you'll see that in its complete detail as we go through this material. Okay, so let's take a look at one particular example, like the one that I just showed you before, and let's see how one might go about finding how to estimate a parameter. So suppose you have a scenario like this. You measure a bunch of data X, various samples of it, and these are equal to some constant plus noise. Okay, and now let's suppose that this guy here is Gaussian with zero mean and sigma squared variance, sampled independently and identically from this distribution. Okay, IID. Okay, so now for the simplest case, let's say you just have one sample. So you have one sample. Okay, let's call that just X1. Okay. Now let's take a look at what the probability density is for this one sample here, given some value of theta. Now I'm writing this as a conditional because I'm going to assume that this distribution is going to be parameterized by the values of theta, which I don't know. Okay, so of course this is going to be 1 over square root of 2 pi sigma exponential minus 1/2 this x1 minus theta squared. Okay? Okay, so if I plot this, of course I'm going to get a Gaussian that is going to look something like this. Okay? Now, suppose I had only two parameters, two values of this parameter to choose from, right? I don't know what theta is, but I know that it's either, let's say, 1/2 or it's 5. Okay, we just have two parameters. So let me plot what this distribution would look like for those two different parameters. Okay, so if theta equals theta 1, then the distribution might look like this. Okay. On the other hand, on the same axis, so let's say this mean here was 1/2. Okay. On the other hand, if theta is equal to theta 2, where this theta 2 is, let's say, 5, then this distribution might look like this. This is 5, for example. Okay? All right, now I have these two distributions. And now let's say I actually look at the value of the data point that I collected. Right? So I collect the data point x of 1, and that value is 4.9. Okay? It's here. Which one of these parameters do you think is the answer? 1/2 or 5? 5, right? Because this value landed where most of the mass of this probability is. Okay? So in other words, one way to estimate parameters is to look at which one of them gives the most likely density function. Okay? So this is a very general framework called maximum likelihood, and we'll see that a little bit later. And we will go through all the details of maximum likelihood later on, but I just wanted to give you an example of some of the different ways that one can go about computing these parameters. Okay, now let's go back to our simple example and kind of analyze how something like this would perform. So let's go back to this example where you had x of n is equal to a plus w of n. Okay? And let's say I'm going to assume that the expected value of Wn is 0, and the variance of this W of n is sigma squared. Now, I'm not necessarily going to assume that this W is Gaussian. Okay, so let's see what happens if I just take this estimator A hat, and I take 1 over n, the summation of x of n, say n equals 1 to capital N. Okay? This is just some estimator. Okay? I have not said anything about whether this is a good estimator or a bad estimator. I'm just saying it's an estimator. Now let's study its properties. First of all, on average, what does this estimator give you? On average, does it give you the right answer? The way I find that out is by computing the expected value of the estimate. And this is the expected value of 1 over n, sum n equals 1 to n, x of n. And of course, this is going to be 1 over n times a, which is a. Okay? So that's the right answer, right? So this is a somewhat arbitrary estimator that I picked, and it turns out on average, it gives you the right answer. The estimator that on average gives you the right answer is called an unbiased estimator. Okay? So this is what we call unbiased. Okay, but just because it gives you the right answer on average, it still doesn't mean that it's a good estimator, because for any given set of data, it might give you an answer that is way off, above or below the right answer, even though on average it gives you the right answer. Okay, so how do we measure the variation of this estimator with respect to the data? The way we measure that is using the variance. Okay, so the variance of a hat is, this is the variance of 1 over n, summation of xn. This 1 over n comes out as 1 over n squared times the variance of the sum of xn. I forgot to mention here, I'm going to assume that the Wn is IID, even though I'm not assuming that it's Gaussian necessarily. Okay? Okay, so if that's true, then the variance of the sum is just the sum of the variances. So this becomes 1 over n squared times sigma squared times n. So this is sigma squared over n. Okay? And what does it say? It says that the more data points you have, the variance of A, in other words, how much it could oscillate around this mean, around the right answer, is related to how many data points you have. The more data points you have, the better. And of course, it's related to how much noise you have. So the more noise you have, the more it's going to oscillate around that average value. Okay, so what so this is the estimator variance. So what I'm trying to do here is, through this very simple example, I'm trying to show you that there are two fundamental quantities that you have to worry about whenever you talk about an estimator. The first one being the bias, and the second one being the variance. Okay. And so let's see now where we go with this. What do we learn from this trade-off? Okay, so let me make some formal definitions here. So the bias is B of theta. This is the expected value of theta hat minus theta. Okay? So what you want is this to be 0, right? That would be good. Okay, now the variance of theta hat, this is equal to the expected value of theta hat minus its mean squared. Okay? So theta hat is just some random variable, and this right-hand side is simply the definition of the variance. The random variable minus its mean squared, expected value, that's the variance. All right, so related to these two quantities is something called the mean squared error. Mean squared error of the estimate is the expected value of theta hat minus theta squared. Okay, now I want to draw your attention to the difference between these two. These two are certainly not the same. And they are not the same because expected value of theta hat may or may not be equal to theta. Right? It is so only if the only if the bias is 0. Right? So what I want to do is to show you how this mean squared error is related to the variance and the bias. It turns out the relationship is very simple. This mean squared error is equal to the variance plus the square of the bias. Okay, so let's take a look at how that works. So this is the expected value of theta hat minus E of theta hat plus E of theta hat minus theta squared. What did I do here? I added and subtracted an expected value of theta hat. So it's exactly the same as before. Okay, now I'm going to separate the pieces by expanding this square term. So this becomes expected value theta hat minus E of theta hat squared, okay, plus the expected value of E of theta hat minus theta squared plus 2 times the expected value theta hat minus E theta hat times E theta hat minus theta. Okay? Now this part here is exactly the variance. Right? Just see it up here. Okay? And this part here is exactly the square of the bias. Okay? The expected value here is really not making any difference. This expected value is not doing anything. Okay? Because the expected value is already taken inside, so this thing in the middle is a deterministic quantity. So this term here is the square of the bias. Okay, now it turns out that if you expand this guy out, this expected value turns out to be equal to 0. Okay, and that's not hard to see. You just multiply the terms out and you'll see that this turns out to be 0. Okay? So, the bottom line is for a scalar parameter, theta, the mean squared error in estimating that parameter is the variance of the estimate plus the square of the bias. Okay? So, now it turns out that whatever estimator you pick, suppose you pick some estimate of theta hat equals g of x, this is your data. Any estimator trades off variance versus bias. Okay? So what do I mean by that? Let's say each one of us picks a different estimator, and we go home and we do a big simulation and we come back with our results. If we each plotted our results in terms of the variance of the estimate and the bias of the estimate, what you'll see is that the different choices that we've made have simply amounted to which estimator has the largest variance, which one has a smaller variance, and if you push the variance down, the bias goes up. If you push the bias down, the variance goes up. Okay? So then you can ask yourself the question, is there a happy balance between these two in such a way that the mean squared error is actually as small as possible? Okay? So that's one approach. Another approach is, you know what, I cannot tolerate the bias being anything other than 0. Right? So I'm going to come up with completely unbiased estimators that make this term go to 0. Now if I do that, then how small can I make the variance? Right? There's going to be some limit as to how far I can push this guy down. Right? And even if I don't push this to 0, it turns out there is always a limit to how far I can push the mean squared error down. With a finite amount of data, if the mean squared error is 0, it means you perfectly estimated the parameter, right? In general, with a finite amount of data, it is impossible to come up with a perfect estimate of the parameter, which means there is a natural lower bound to this mean squared error for any problem you consider. Okay? And that's one of the things that we will discuss. There are various different ways to come up with lower bounds to this. We will discuss one particular one called the Cramer-Rao bound. Okay? So any question about this very important idea?
If the mean square error is fixed, then there is a trade-off between variance and the bias, yes?
Well, yes. I mean, that's one way to look at it. Yeah, I mean, if you want to fix your mean squared error at some number, there may be multiple estimators that can give you that mean squared error with different variance and bias trade-offs. That's correct.
So this trade-off is just for the case when the mean square error is fixed?
Well, yes and no. What's also true is that you can have two different estimators that have different mean squared errors. Let's say you come up with an estimator and I come up with an estimator, and your mean squared error is lower than mine, right? It is still completely possible for my estimator to have a smaller bias than yours, or for your estimator to have a smaller bias than mine, right? Even though we don't have the same mean squared error, the bias and the variance can still be different for the two different estimators. But a special case of that is, of course, if we have the same mean squared error, one estimator might be preferable because maybe you don't like bias. Okay. The idea here, the basic idea here is, you may have heard the English expression, there's no free lunch, right? There's no free lunch. If you push the variance down, bias comes up. Push bias down, variance comes up. You got to decide. You're engineers. You're going to have to decide what to do. Okay. So this whole thing, as I described it now, was for scalar variables, right? And as I will, as we go through this material, we will be estimating also vector variables. Okay, so for instance, suppose as an example I write x of n is equal to, again, the same thing, very simple problem, a plus w of n. And let's say this guy, he's very simple. Let's even take it to be Gaussian, IID. Okay, and now suppose my unknowns are both a and sigma squared. Okay, I don't know the mean and I don't know the variance. Now the parameter theta is a sigma squared, which is a vector. Okay, so now my estimator is going to look like this: theta hat with a little bar underneath it. This is going to be a vector estimate of both of these parameters. This is going to be some function g of the data again, and maybe I put an underbar under this. So now this is basically, theta 1 hat, theta 2 hat, and so on. Okay, the same is true if you have n variables that you're trying to estimate. Okay, so how do we define the bias in this case and the variance in this case? This takes a little bit more doing. Okay, so the bias is the expected value of theta hat minus theta. This is just element-wise, right? Theta 1 hat minus theta 1, theta 2 hat minus theta 2, and so on. So this is pretty simple. Now it turns out here, instead of the variance, what we're going to do is we're going to compute the covariance of theta hat. Okay? So let me go back just for a second here. So note here that the variance was theta hat, expected value of theta hat minus e of theta hat squared. In this case, this is going to be a vector. So this is going to be the expected value, theta hat minus e theta hat. These are vectors now. Times theta hat minus e of theta hat transpose. Okay. So this is a vector. This is a vector. This is the outer product of these two vectors. You take expected value, and you get the covariance. Okay. Now, how do we do mean squared error in this case? What we do is we actually define a mean squared error matrix. And that's this way. Expected value, theta hat minus theta, times theta hat minus theta transpose. Okay? You can, in fact, compute the a scalar version of this too, if you want to somehow get an idea of the mean squared error incurred in estimating all the components of theta. Then what you do in that case is you simply consider sort of a diagonal version of this. Scalar MSE is the expected value theta hat minus theta transpose theta hat minus theta. Okay, so the transpose goes here now. Okay, so in this case, this is an outer product of two vectors, so this is the expected value of a matrix. Here, this is the expected value of the inner product of two vectors, so this is a scalar now. And so this is the expected value of a scalar. And what is this equal to? This turns out is equal to the trace of the covariance of theta hat plus B transpose B, where this B is this bias vector. Okay, so let me write it out again a little more clean up here. Scalar mean squared error. Trace covariance of theta hat plus B transpose theta. B of theta. Okay, so in other words, here too, the scalar quantity that you can define as the mean squared error is the sum of two terms, where here the trace of the covariance matrix is what? Is the sum of the diagonal elements, which is summing up the variances for each of the components of theta that you've estimated. Right? And this is the inner product of the bias terms. So this is the square of the bias for the first element plus the square of the bias for the second element, and so on. Okay, this is just a very compact way of writing it. Okay. So now let's see if we can somehow come up with, let's go back to the scalar case and see if we can come up with estimators that somehow have minimum mean squared error. Now let me first warn you, if we go back to this definition of mean squared error, if you look at this definition of mean squared error here, what does it involve? It's the expected value of the estimate, which depends on the data, minus the true value of theta. But you don't know the true value of theta, right? So if I try to come up with the estimator that has the minimum mean squared error, I'm implicitly assuming that somehow I have knowledge of the truth, right? Which I don't. So what you can see is by simply looking at this, you should generally expect that minimizing mean squared error is a very difficult thing to do, because the expression immediately tells you it requires sort of clairvoyant knowledge of the thing you're trying to estimate, right? Okay, so don't expect too much if you want to minimize mean squared error. And if you don't expect too much, then what you're going to end up doing is to make these other compromises. Well, maybe I'll set the bias to 0 and then try to make the variance as small as possible, etc. Okay? In a few exceptional cases, you will be able to minimize mean squared error, but not necessarily in general. At least not in the formulation that we've written down. Okay, so let's do a particular example that maybe will illustrate this in one form. All right, so again, our simple problem, say A plus Wn. Again, the mean of these guys is 0, the variance sigma squared, and their IID. Again, I'm not going to assume that it's Gaussian, okay, but just these things. Okay, so now let me, this estimator that we had before, right? 1 over n summation of x of n, okay? This is what we had before. I'm just going to make this estimator a little bit different. I'm going to put a constant in front of it, little a. And I'm going to play with this constant to see if I can somehow minimize mean squared error. Okay, let's see what happens. Okay, first of all, what's the bias? The expected value of a hat, the expected value of a 1 over n summation x of n. Okay, so the a is just some constant I'm going to play with, comes out, so it does 1 over n. This thing we computed before, so this is a times capital A. Okay. So the estimator is no longer unbiased. It's actually biased because the a, unless I pick a to be 1, which is just what I had before, then it's going to be a biased estimator. Okay? So the bias, b of a, is a times capital A minus capital A. So a minus 1 times capital A. Okay? All right, what about the variance? Variance of a hat, variance of a 1 over n, sum xn. So this is a squared 1 over n squared, variance of the sum. Okay, so you simplify this and you get a squared sigma squared over n. Okay? Because this guy here is n times sigma squared, one of the n's cancels, and this is what you get. Okay, so therefore mean squared error is a squared sigma squared over n plus a minus 1 squared a squared. Okay? Yeah? Question? Okay, now what I wanted to do is to minimize mean squared error. I have this parameter to play with. So the way I'm going to play with it is I'm going to take a derivative of this guy with respect to a, set it equal to 0, and see what I come up with. Okay? So what you want to do is to pick a such that the mean squared error is minimized. Let's do that here. Give that for a second. Okay, so differentiating the mean squared error with respect to a, 2a, oops, you can't see that, can you? Okay, 2a sigma squared over n plus 2a minus 1 times a squared. You set this equal to 0. And you can check the second derivative also to make sure that you in fact are getting your minimum. Solve this for little a, and you get this a star. The optimum a is a squared over a squared plus sigma squared over n. Hey, looks great, right? This will minimize the mean squared error. Anybody see a problem with this?
You do not know.
Yeah, it depends on capital A, which you're trying to estimate.
It also depends on the sigma power, on the sigma energy. And that is something.
Are you talking about this?
Are
Are you talking about this?
Yeah.
Well, this is not the signal, this is the noise.
The noise, yeah, but
Right, but we're assuming we know this part. Okay? So these are the assumptions I made. I know these things.
right, but you can refactor that to 1/1 plus the SNR.
Yeah?
And that is something that we can measure.
Not exactly. The SNR, you can only know it exactly if you know the signal. Okay? The point is you're trying to estimate the signal. And if you don't know the signal exactly, you don't know the SNR exactly. SNR is nothing but this, signal energy divided by noise energy. So don't know the signal, you don't know the noise. Okay. The bottom line here is that the optimal value of A depends on something you're trying to estimate. Therefore, this is unrealizable. Okay, so we somehow fooled ourselves into thinking, okay, we could minimize the mean square error by playing with this parameter, but at the end, the parameter ended up being dependent on the thing we're trying to estimate. You kind of got the circular argument. It's not going to go anywhere. Okay. Now, in some cases, it turns out you can get away with this. And here's an example. So, second example. Let's say the data is just a noise sequence. The same assumptions as before. Zero mean, variance is sigma squared, and zero variance is sigma squared. IID, except that I'm going to assume this is unknown. Okay, so I want to estimate the variance now. The noise power is what I don't know. Okay, so let me propose the following estimator. Say sigma squared hat is A times 1/n, the sum of x squared n, n equals 1 day. Okay, so I'm going to estimate the noise power by taking the average signal power and multiplying it by some constant, and then again playing with that constant. Okay, see if I can minimize the mean squared error. Now I'm going to skip the calculations, and I'm just going to show you what the mean squared error looks like. The details are very much like the one we did before. So you get 2a squared sigma to the 4th divided by n plus a minus 1 squared sigma to the 4th. And again, you want to minimize this with respect to A. So your A star is going to be, this is how we write this, arg min, argument that minimizes over A the mean squared error. Okay? I'm just teaching you a little notation here, so this is nothing fancy. And it turns out that this is n divided by n plus 2. Okay? In other words, magically, the A star actually does not depend on the unknown parameter. So if you want to come up with an estimator for the variance, for the noise power, that has minimum mean squared error, then you replace 1/n with 1/n plus 2. Okay, you see what happens if you multiply here. The n goes away, the denominator becomes n plus 2. Okay. Now, in fact, in practice, we don't often use this estimator because we don't like estimates of noise power that are biased. Okay. Typically, we want to come up with estimators that are unbiased, and it turns out that if you want an unbiased estimator, then replacing the 1/n with 1/n minus 1 is the correct thing to do. That way, you get an unbiased estimator, which is not minimum mean squared error, but at least it has this nice property of being unbiased. Okay? So for instance, if you want to estimate the variance in MATLAB, right, everybody knows that there's this function STD, right, standard deviation. But it actually has a couple of arguments. I don't remember exactly what the arguments are, but one of them will allow you to compute the variance with a 1 over n factor in front of it. The other one will allow you to compute it with a 1 over n minus 1 factor in front of it. Okay? So next time you use the function standard deviation, think about that. Okay. Okay. Any questions so far? You don't seem happy, Andre.
No, I mean, this is basically just S squared from stats.
Which one?
The sigma squared hat.
This one?
Yeah, you can use.
Yeah, if you get rid of A,
No, I
then-
mean, I guess the optimal estimator for that. When you have a random data set that's not infinite.
yeah, this is called the sample variance. Yeah, without the A, it's just simply the sample variance. Yeah, that's exactly what MATLAB will do as well. If you just say STD of a long vector, what it will compute is this. Default will compute I believe the default is this. And then if you change the argument, you tell it, compute it in this other way, it will replace this with n minus 1. Okay, and that will become an unbiased estimate. Okay, so let me summarize what we just talked about. So mean squared error, theta hat, is the variance, theta hat, plus the square of the bias. By the way, I want to emphasize a notational issue here. You will see me often write the variance as a function of theta hat, whereas the bias I will write as a function of theta. Okay, why do I do that? I do this because I want you to remember that the bias, in general, is a function of the underlying parameter. Okay? So in other words, you generally won't know exactly what the bias of your estimator is unless you somehow know the underlying estimate, the underlying value of the estimate. Okay? On the other hand, the variance is just a function of the estimate. It's just a function of theta hat, which is a function of the data. Right? So this does not require you to know the underlying value. Okay. All right, so let's see what compromises we might take. Possible trade-off might be to choose estimator that is unbiased and has minimum variance. Okay? So I can ask the question, is it possible for me to come up with an estimator that has no bias and its variance is as small as possible? Okay? Is that the same thing as minimizing the mean squared error? It is not. Okay? I don't want you to confuse the two things. Because it is possible for me to give up on the variance and let the variance go up and actually get a better estimate. Okay? So, if you are able to do this, the resulting estimate is called minimum variance unbiased estimator, or MVUE for obvious reasons. Okay? Now, you might ask the following perfectly reasonable questions. Does the minimum variance unbiased estimator always exist? Is it always possible to set come up with an estimator that has no bias and the smallest variance possible? And the answer is no. Okay? It may not be possible to make this compromise, which is why we don't have only one kind of estimator. We have many different kinds of estimators. We have the MVUE when it exists. We have maximum likelihood. We have something called maximum a posteriori. We have Bayesian estimators. You'll see all of these later on. Okay, so that's one question. Second question, if this minimum variance unbiased estimator exists, how to find it? Okay, Okay, I could maybe come up with a proof that says such an estimator exists, but that proof will, in all likelihood, not tell you how to find it. Okay? The next question might be, again, if this minimum variance unbiased estimator exists, how small can its variance be? Okay. If these things exist, maybe there are multiple estimators that have zero bias, right? Maybe there's several of them, the whole class of them maybe. Okay. And then you have the following question. Each one of those estimators that is unbiased might have a different variance, right? And one of those estimators is going to have smaller variance than the other ones. Is it fair to say that the one that you found that has a smaller variance than the other ones is the best possible? Maybe tomorrow somebody will come up with yet another estimator that has zero bias and even smaller variance. Well, just intuitively, you probably will not find an estimator that has zero variance, right? If the bias is zero and the variance is zero, you've perfectly estimated the parameter, and that's not going to happen, right? So there is going to be a floor below which this variance is not going to go, right? And that floor is what we call a lower bound, and this is determined by, there are various ways to study it, but one way to study it, which we will consider in this course, is very popular. It's called the Cramer-Rao lower bound. This Cramer-Rao lower bound turns out to have a lot of really interesting properties, not only because it tells you how small you could make the variance of the estimator, but also it often gives you, as a result, a lot of insight as to how hard the problem is, right? I mean, if you computed this lower bound, and the lower bound was actually a very large number, what does that tell you? It tells you the variance can't go below a very large number. In other words, it's really difficult to estimate this parameter. On the other hand, if you computed the lower bound, and the lower bound was like really close to zero, then it says, you could probably get a really good estimator. Okay, so it's a very nice analytical tool for studying the problem fundamentally, regardless of what algorithm you use. Okay? These bounds will be valid for any algorithm you use to estimate your data. Okay, as long as, for example, the unbiased condition is satisfied. There's also a biased version of this, which I will get to, but I don't want to rush into it right now. Okay. So, the next thing we're going to talk about is, in fact, this Cramer-Rao bound, and I don't want to just give you the equations for it. I want to motivate it again. So let's spend some time doing that. The Cramer-Rao lower bound, there's in fact two cases for this as well. You can study the unbiased and the biased case. So I'm going to do this one first. Okay. So I just showed you the minimum variance unbiased estimator was just about how far you can push the variance down. It turns out that this biased version, in fact, is a lower bound on how far you can push the mean squared error down. Right? Even if you let yourself have bias, you still won't be able to hit a zero mean squared error. So what's the floor for that? It turns out the same analysis will give you that case as well. Okay. So let's take a look at an example and see if we can motivate this Cramer-Rao bound. So again, let's say x is equal to a constant plus w. Okay, and let's say the w is Gaussian, zero mean sigma squared. Okay. For now, let's just say a single value, right? Single data point. Okay. So let me draw the distribution for this for this x. So PDF of x given a. I'm going to draw it in two different situations. one where sigma squared is relatively small, and one where sigma squared is relatively large. Okay? Now, of course, the mean in both cases is A. Okay, so this is sigma squared large, and this is sigma squared small. Okay? Now let's write down the probability density function. df of x given A is 1 over the square root of 2 pi sigma, which is minus 1, 2 sigma squared x minus A squared. Okay? And let me take the log of this. Log of PDF of x given A is equal to minus the log of square root of 2 pi sigma, 2 sigma squared x minus A squared. Okay. The log really doesn't do anything aside from making the calculations a little simpler. So that's really not a big deal. But the point is, what I want to do now is to look at this function here, which is a quadratic, and think about how it varies as a function of the unknown parameter A. Okay? In other words, I want to see how sensitive this function is to changes in the values of A. Okay. One way to measure sensitivity of a function with respect to a parameter is to look at its derivatives. First derivative and the second derivative. Okay. So let's take a look at the derivative, the first derivative. This is 1 over sigma squared x minus A. And then if you compute the second derivative, let's put a negative sign in front of it. This is 1 over sigma squared. Okay? Now I put a negative sign in front of it because I know that this is a maximum as opposed to a minimum, so because it's a maximum, the second derivative would turn out to be negative, so I move the negative to this side. Okay. All right, so now going back to these two pictures. In which situation do you think it is easier to estimate the parameter A? In which case would you get a better estimate of the parameter A given your data point? Obviously, in the case where the noise is small, right? Okay? So, in this case, you would get a better estimate. In this case, you'd get a worse estimate. Now, look at what this tells you. For this very simple example, this second derivative is inversely proportional to the variance, right? So what does this tell you? This is basically telling you something about the curvature of this curve at this peak. Okay? In other words, if sigma squared is very small, the curvature at this point is very high. And that means the estimate is going to be better. On the other hand, if this thing is really big, the curvature becomes very flat, which means it's very difficult to estimate the unknown parameter. Right? Now what I've done here is I've shown you this very, very simple example, but it turns out this quantity here is the key to measuring how good you can, how well you can estimate a quantity or how good your estimator can be, which is related to this Cramer-Rao pattern. Okay, so let me write down the more general situation. So this quantity, log of p, x given theta, this thing is basically giving you some idea, gives you some indication of the difficulty of estimating theta. Okay. Now there's one problem with using this. In this case here, you didn't see the problem because it was so simple. This quantity here did not depend on the data in this case. Right? Somehow the effect of x just went away when I took the second derivative because the model is so simple. In general, however, this quantity turns out to be a function of x. Okay? X doesn't drop out. So what's the natural thing to do? You don't want your performance measure to be a function of every single data point. What you want is some kind of average performance measure. You want to measure somehow the average curvature around this peak in a way that doesn't depend on the specific data point that each time you got. And so the natural thing to do is you take expected value of this. You take the expected value of this quantity minus second derivative x given theta. And this is expectation over x. Okay? So this quantity here no longer will depend on the specific data point that you've measured. Okay? So writing this a different way, this is equal to the integral minus the second derivative x given theta, theta squared times the PDF of x given theta dx. Okay? This quantity, which is the same as this guy here, this measures the sensitivity, of the PDF, of this joint PDF of the data to changes in theta. Okay? What it means is that large sensitivity means that it's easier to estimate the parameter. Let's think about that for a moment, just from an intuitive point of view. If the shape of the probability density function changes a lot with a small change in theta, what does that tell you? It tells you theta has a huge influence on what your data is going to look like, right? And taking the argument now backwards, if your data is very sensitive to the value of theta, therefore theta should be easy to get from the data. Okay? Let's take the reverse argument. If your data is not sensitive at all to the value of theta, what would happen? You would keep measuring data. You would always measure the same data, even if the underlying theta is just changing wildly. You cannot estimate. Okay, so that's sort of the reverse of this argument. Okay, so large sensitivity give you a good estimate of theta, or better estimate of theta, easier to estimate theta. Okay. All right, so let me now state what is the Cramer-Rao lower bound, and then I will try to see if in the next 20 minutes or so we can prove it, and then we'll do lots of examples and so on next time. Okay. So here's the theorem, and we're going to prove it, and the proof is not very difficult. So this is the Cramer-Rao lower bound for scalar parameters and unbiased estimators. Okay, what it says is the following. Suppose that the PDF of x given theta satisfies the following condition. The expected value of the derivative of the log of the PDF is equal to 0. This is not a weird condition at all. Turns out this condition is almost always true, except when the PDF behaves very strangely. Okay, so this is not a very onerous or difficult condition to satisfy. But suppose that it is satisfied, then the variance of any unbiased estimator theta hat satisfies the following. The variance of theta hat is less than or equal to 1 over minus the expected value of the second derivative of the PDF, log of the PDF. Okay? This is what we called this sensitivity quantity, and it turns out this denominator here is called the Fisher information. And it's named after a very famous statistician called Fisher. Okay? So the reason this denominator is called information is because the variance in the estimate is an indicator of the quality of the estimate, right? And so the more information you have about the parameter, the larger this denominator will become, and the smaller this lower bound becomes, which means that this variance can get closer to 0. Okay? All right. There's a biased version of this as well. And let me just write it down. We're not going to really use it very much, but so the biased version is actually a bound not on the variance but on the mean squared error. Mean squared error, function of theta hat. This is lower bounded by. The denominator here is the same as there, so this is the Fisher information. Okay, same thing here. The numerator is the derivative of the expected value of theta hat with respect to theta squared plus the square of the bias. Okay? So what happens is, if you look at the difference between these two, the denominator here is the same. This term is missing because here it's the unbiased case. And the numerator is going to involve the derivative of the expected value of theta hat with respect to theta squared. If the expected value of theta hat is simply theta, then this derivative is 1. Because d theta is 1. Right? So this just defaults back to this case. Okay? I'm not going to prove this. I'm just going to do this one. Any questions about this? Okay. So what you see here is that the mean squared error is in fact, the lower bound to the mean squared error is sensitive not just to the bias, but also to the derivative of the bias. Okay. This is really related to the derivative of the bias. Okay. Which is something you probably wouldn't have expected starting off. Okay, so let's now try to understand this Cramer-Rao bound proof. This is, again, I'm going to do this for the unbiased case. Okay, in order to do this, there's a couple of things we first need to define. When you take the log of the PDF with respect to the parameter, this is called the score function. Okay, this is just a definition. Okay, so of course another way to write this is dp d theta times 1 over p of x given theta. Right? Derivative of the log. Oops, there's a partial derivative here. Okay. The derivative of the log is just the derivative of the function inside the log divided by the function. Okay. All right, so if you remember in the previous page when I wrote this condition, this regularity condition, so-called regularity condition, it seemed like a little out of place, a little odd to be making this assumption, but this is really just the expectation of the score function, right? And I said I want this to be 0, but it turns out in general it is 0, so let me show you how that works. Let's take the expected value of S. I'm going to consider the simple case where the x is going from minus infinity to infinity. Okay, so it's the score function here, dp x given theta d theta times 1 over p of x given theta times p of x given theta dx. Right? Okay, this cancels that. Right? And so if you look at this derivative, this integral as a whole is equal to 0. Okay. Why? Because I can pull this derivative theta out of the integral, and then I just have the integral of p of x given theta dx. That's equal to 1. So maybe I should write it out explicitly. These two cancel out. This becomes d by d theta of the integral p of x given theta dx minus infinity to infinity. This, by definition, is equal to 1. Right? So this derivative is simply 0. Okay? So what this shows you is the expected value of the score function is always 0, which is what I had here as my regularity condition. So no big deal. Unless this p behaves really strangely, and I can't pull this derivative out of the integral. Right? There's highly technical things have to happen in order for me not to be able to reverse the integration and the differentiation here. Okay? Otherwise, this is equal to 0. Okay. Now, another property of the score function is that what I wrote down here is just for a single data point, because the integral here was just, over a scalar, right? Now, what happens if I want to write the score function for a bunch of data points? Okay, so this is maybe a single data point. Okay. So let's take the score function for x1, x2, xn. Okay. So this is d by d theta of the log of the PDF of the joint PDF of x1, x2 through xn given theta. Right? Okay. Now, if the data points are independent, x1 through xn are independent and identically distributed, okay? Then this integral, this derivative, I can write it as d by d theta of the log of the product p of x1 given theta times p of x2 given theta, and so on, p of xn given theta. Right? Okay. Now it's the log of a product. That turns out to be the sum of the logs. And therefore, what I have here is I get a bunch of individual terms, I equals 1 to n, d by d theta of the log p of xi given theta. Okay? This is the score function for each of the data points. So the score function for all the data points is simply the sum of the score functions for each of the data points. Okay? Now, the score function has this nice property. In fact, its variance, so the variance of the score function, this is the Fisher information. It's not obvious yet because the variance of this quantity, I call Fisher information here minus the expected value of the second derivative. but I'm calling it the variance of this quantity. It turns out the two are exactly the same. I'll show that to you a little bit later. Okay? So what's nice about this is the score function is variance gives you the amount of information contained in the data about your parameter. And furthermore, it shows you that that if you have independent data, the information gets added together, right? So the information contributed by each of the independent samples is simply added to the information from the rest. Okay. All right, so now with this sort of preliminary thing in place, we can proceed with the proof. Before this, let me just recall, I hope you all know this, but if not, that's okay too. If you have two random variables x and y, the expected value of x, y squared is less than or equal to the expected value of x, expected value of y. Okay? Sorry, expected value of x squared, expected value of y squared. Okay? So this is simply called the Cauchy-Schwarz inequality in analysis, in mathematical analysis. And what it simply says is that if you take the inner product of two vectors, the square of that inner product is less than the product of the squares of these two terms. Okay? All right, so with this, let me start from the top of the page here so that we can see how everything goes. So I can take the expected value of the following quantity, s minus e of s, so this is the score function, times g minus e of g. I'll tell you what g is in a second. And then this whole thing squared. So g is theta hat is g of the data, okay? So this g is just the estimating function. We just call it theta hat as well. Okay, so this guy here is less than or equal to the expected value of s minus e of s squared times the expected value of g minus e of g squared. Right? Okay? This is just the relationship that I wrote here. X and y are simply this guy and this guy. Okay, and everything is a scalar as far as we're concerned. Okay, so now I'm going to multiply this left-hand side and kind of expand it and play around with the right-hand side as well and see what we get. This, by the way, is simply the variance of theta hat, right? Because g is just theta hat. Okay, so let's rewrite this. The expected value of s, okay, let me just go back to writing this as theta hat because I think I've already confused you by rewriting the g as a theta hat. So this is just theta hat, okay? All right, so s times theta hat minus the expected value of s times theta hat plus expected value of s, expected value of theta hat, and then this whole thing squared. This is expanding this guy. This is less than or equal to the expected value of s squared minus 2s e of s plus the expected value of s squared times the variance of theta hat. Okay, I just expanded this guy here. Okay? So I've multiplied these out. That's this left-hand side. And then the right-hand side is expanding this guy out. All right, so what's going to make things simple now is the fact that let's see, where is it? Is the fact that the expected value of s is equal to 0. Okay, so we're going to use this. This is going to be going to 0. Let's see, I think I might have copied something down wrong here. Expected value of s. I said one term missing, right? Yeah, I'm missing a minus s times the expected value of theta hat here. Right? Okay. All right, so this term is going to go away, and this term is going to go away. And here, this term is going to go away. So what do we get? Expected value, this is going to be squared of s theta hat minus s expected value of theta hat. This whole thing squared is less than or equal to expected value of s squared times the variance of theta. Okay? Okay, this is what we called the Fisher information, right? I told you earlier the variance of S was the Fisher information. Okay? So I'm just going to rewrite this in a slightly different notation. It's called I of theta. This is the Fisher information. Okay, and then the next steps are just, further simplifications of all of these things. So let's see. This becomes expected value of s theta hat minus expected value of s expected value of theta hat, the whole thing squared, less than or equal to I of theta times the variance theta hat. Okay? Now, this is simply the expected value is spread across these two terms. And the expected value of s and expected value of theta hat, this is just a constant, so it just comes out, and you see it over there. Okay? So again, this part will go away. Okay? So this becomes expected value of s theta hat, the whole thing squared, is less than or equal to I of theta times the variance theta hat. Okay. This is really the only long proof that we're going to do in this class, and it's a worthwhile one to do because you see lots of different properties being used here. So let's finish it up. Okay, so now I can write this whole thing. Let's see. I'm going to write it as an integral so that we can see more clearly what's going on. This is the integral. This whole thing is going to be squared minus infinity to infinity dp x given theta d theta times 1 over p of x given theta times theta hat p of x given theta dx squared. So this is the right-hand side. I'm sorry, the left-hand side. Okay. So let me just write this. This is the left-hand side. Okay. Once again, I'm going to play the same trick that I did before. I'm going to take this derivative and pull it outside and simplify. So I get d by d theta integral minus infinity to infinity theta hat p of x given theta dx, this whole thing squared, so less than or equal to I of theta variance theta hat. Okay? And what is this? This is the expected value of theta hat, right? This whole thing is the expected value of theta hat. So this is d by d theta, expected value of theta hat squared, less than or equal to I of theta, variance of theta hat. We said this was unbiased, right? So this is theta. So d theta is 1. So this becomes 1 less than or equal to I of theta, variance of theta hat. And so therefore, the variance of theta hat is 1 over the Fisher information. Okay? So it's clearly not an obvious result, right? But an awfully useful one. And I didn't even do the biased case. The biased case is, involves even more calculations. But this is the bottom line. Okay? Now, just to kind of put things in perspective a little bit, I don't think we have enough time to go through any more details, but I just want to remind you what the Fisher information is and how we defined it in 2 different ways. Okay, that's this I of theta. One of them was that it's the variance of the score function. Okay, and if we look at what the variance of the score function was, it's the expected value of the log of p x given theta d theta squared. Okay? But we also defined it as minus the expected value of the second derivative of this function, right? Again, it's not at all obvious that these 2 things are the same, but they are, and let me show it to you. It will take 2 minutes. You start with this expected value. We know the expected value of s is equal to 0, right? What does this say? Expected value, the log of p x given theta d theta is equal to 0. This is a constant, and therefore I can take a derivative of it with respect to theta and set it equal to, and that's going to be 0 too. So d by d theta of this quantity, which is an integral log d log p d theta times p dx. This is equal to 0. Okay, this is simply this expected value. Okay, and what I'm going to do now is going to do the reverse of what I did before. Before I kept pulling the derivative out of the integral. Now I'm going to push the derivative inside the integral. Okay, push the derivative inside the integral. What you get is the integral of the second derivative of log of p d theta squared times p plus dp d theta times d log p d theta, and then this whole thing dx equals 0. Okay, so when I push this derivative inside, I have the product of 2 terms. This is just the product rule for the derivative. Okay, and finally, okay, so let me put this here. Okay, what I want you to remember is this dp d theta, I can write this as d log p d theta times p. Okay? Because the derivative of the log would be just this times 1 over p, so I just move the p to the other side. Okay? So then this whole thing becomes the integral of the second derivative of the log likelihood times p dx plus the integral of log p d theta squared times p dx. And this thing is equal to 0. Okay? And what is, these 2 things are simply the 2 quantities that we are interested in. The first one is the expected value of the second derivative of the log likelihood function plus the expected value of the square of the first derivative. And this is equal to 0. Okay? And this is exactly the same as what I wrote up here, which is that these two things are equal. Okay? All of this followed from the simple idea that the expected value of the score function is equal to 0. Okay, that's really the only assumption we needed to make. All right, so it's actually fairly important to remember that these two things are equal, because what that allows you to do is, if you're asked to compute the Fisher information, you can either do it this way or do it that way, and it turns out one of those is usually much easier than the other. Okay, so it's good that you have two different ways to do it. Okay, I think we'll stop here. So please don't forget to turn in your homeworks.
Are you going to
2:30. I don't have my calendar in front of me, but yeah, if I have office hours, yes, then I'm available. Yeah. I thought my office hours were Thursday. Yeah. Come on over anyway. Oh yeah, well then that's right. I guess I haven't set fixed office hours. Why don't you send me an email and make sure I don't have something on my calendar.
Okay. Then I know this isn't MATLAB, but this is the equivalent Monte Carlo. Or do you want me to redo this in MATLAB?
No, what did you do it in?
Mathematica.
Mathematica? No, it's fine. The thing is, I don't know how to read Mathematica. You know what I mean? I mean, I don't code in Mathematica.
I added in all those comments.
Yeah. This is fine for this time, but I really want you to learn to do it in MATLAB.
Okay.
Because if you're going to be analyzing data, you're going to be analyzing it in MATLAB, not in Mathematica. Okay, so I'll accept it this time, but next time, please try to do it in MATLAB. Or definitely do it in MATLAB. Don't just try. Yeah.
Is this a lower bound and achievable lower bound? Or
Not always. No, not always. It depends on the problem. So if you come up with an estimator that achieves the lower bound, then it's called an efficient estimator. But an efficient estimator doesn't always exist. Sometimes you have problems where there is no way you're going to hit it. Now, it may be possible to achieve the lower bound for specific values of the underlying parameter, but not for every value. Right? So the lower bound is going to be a curve, and the variance of your estimator is going to be some other curve. The definition of efficiency is when these two curves touch.
Yeah.
Everywhere, right? Well, it's possible for the curve to touch at one point. That's not generally called an efficient estimator. It's just, locally efficient. It's just at one point. Okay? So no, it's definitely not always achievable.
Thank you.